Hey guys, welcome back. My name is Cesar Hernandez. I'm here to talk about gradient descent and generalization. We're going to go over an introduction about gradient descent, what is generalization, and conclusions for each. Starting off with gradient descent. So we're going to explore the concept of gradient descent, which is a fundamental algorithm that enables neural networks to learn by adjusting weights and biases based on training data. It discusses the structure of neural networks, the cost function, and how gradient descent algorithm minimizes the cost to improve classification accuracy. What is gradient descent and how is it helpful? So what is gradient descent? Gradient descent is an optimized algorithm used to minimize the cost function by adjusting a model's parameters, which are its weights and biases over time. It's finding the lowest point in a landscape of errors, helping a neural network learn from the data. An analogy I like to think about this is imagine you were hiking down a foggy mountain. The cost function. So the first step in the learning process is defining a cost function, which quantifies how well the network is performing. Initially, when weights and biases are randomly set, the network's output will be inaccurate. The cost function measures the differences between the network's output and the desired output. Summing the squares of those differences for each training example, a lower cost indicates better performance. The gradient descent algorithm is used to improve the network's performance, which is used to adjust the weights and biases based on the cost function. This is where gradient descent comes into play. The algorithm involves the following: initialization, cost calculation, gradient calculation, weight adjustment, and iteration. So initialization starts with a random weights and biases. The cost calculation computes the cost function to evaluate performance. The gradient calculation determines the gradient of the cost function, which indicates the direction of the steepest ascent. Weight adjustment adjusts the weights and biases in the opposite direction of the gradient to minimize the cost function, and iteration repeat the process over and over. Backpropagation. Backpropagation is the efficient computation of the gradient is achieved through an algorithm called backpropagation. The algorithm calculates the gradient of the cost with respect to each weight and bias, allowing the network to learn from each training example. The goal is to minimize the cost function, which reflects on the network's performance across all training data. Learning outcome. In summary, the learning process of a neural network involves minimizing the cost function through gradient descent. This algorithm allows the network to adjust the weights and biases based on training data, leading to improved classification of accuracy. However, the network's internal working may not align with our intuitive understanding of how it recognizes pattern. Understanding these concepts is crucial for delving into more advanced neural network architectures and their applications in modern machine learning. Now, I'll talk about generalization as the broad. So in context of machine learning, generalization refers to a model's ability to perform well on new unseen data after being trained on a specific data set. It's a measure of how effectively the model has learned the underlying patterns in the training data and can apply this knowledge to make accurate predictions on data it hasn't encountered before. So, what is that we're generalizing? What does that mean in a neural network? What is generalization? Generalization in a machine learning refers to a model's ability to perform well on new unseen data after being trained on a given data set. It is a key indicator of whether the model has truly learned meaningful patterns or simply memorized the training examples. The randomization in the training of neural networks. Randomization is crucial during training. It is helpful because it prevents overfitting and helps model generalize better. The weight initialization of a neural network starts with a randomly initialized weights. This ensures that different neurons learn different features rather than all converging to the same solution. Data shuffling. Training data is often shuffled to avoid bias in the order of samples, ensuring the model doesn't memorize the patterns based on sequence. The importance of a training set in the model's performance is used in a large data set consisting of diverse examples to learn meaningful patterns. The size and quality of data, a larger, more diverse training set helps improve generalization, meaning the model can perform well on new unseen data. Bias in distribution, if the training set is biased or unrepetitive, the model may struggle to generalize and might overfit the certain patterns. The impact on generalization, a well-randomized and properly structured training set helps the model learning underlying structures rather than just memorizing examples. A proper data augmentation and pre-processing such as shuffling, noise injection, and dropout techniques further help generalization. So the overall learning outcome is randomization plays a key role in training neural networks by preventing overfitting and improving generalization. Weight initialization ensures neurons learn distinct features, while data shuffling prevents the model from memorizing patterns based on sample order, so in sequence. The training set significantly impacts model performance. A large and diverse data set helps the model generalize better, whereas a biased or unrepresentative data set may lead to poor performance on a new data. To enhance generalization, model benefits from proper data augmentation and pre-processing techniques such as shuffling, noise injection, and dropout, which help the model learn robust features instead of memorizing examples.